Okay, question 12 asks us to show that the x-coordinates of the turning point of this curve satisfy this equation. So they're asking us to differentiate, find the stationary points, so differentiate it and set it equal to 0. We've got a product here, so we're going to be using the product rule, which is to differentiate the first term. And if you remember, if you differentiate e to the kx, that turns into k e to the kx. So the minus 0.25 is going to come to the front and times by the 10. So that's going to be negative 2.5 e to the negative 0.25x. And then we're going to times that by the second function not differentiated. And then add on the other way around, so leaving this one alone and differentiating the second one. So that's going to be 10 e to the negative 0.25x times by cos x, because when you differentiate sine x you get cos x. I'll get that out of the way. So times by cos x. We want the turning points, so we need to set that equal to 0. So at turning points f dash x equals 0. So if we set this equal to 0, we've got, and I'm going to rearrange it, so we've got the positive value first, so 10 e to the minus 0.25x cos x minus 2.5 e to the minus 0.25x sine x needs to equal 0. I can take out a factor of let's take out a factor of 2.5 e to the minus 0.25 x, which gives me 4 cos x here, and then minus sine x here. So to find the turning points, because we've now got a product equaling 0, either this is 0 or 4 cos x minus sine x equals 0. However, an e function is never equal to 0. The graph of e doesn't ever hit the the x-axis, so that's never 0. So there's no solutions from that one. This one we can get solutions from. If we add on the sine x and divide by cos x, we've got 4 equals sine x over cos x, and sine x over cos x is tan x. So that's what we're aiming for. That's what they had in the question. So that's part A done. Okay, part B then says, well, here's the graph of the function, and it wants us to sketch the modulus of that graph. So I'm going to use the graph we've got here and just draw over it. What's going to happen is this is going to stay as it is, but then when this goes negative, that's going to flick back up to the positive side. So I'm going to have a point like this. This is going to be exactly the same. Try and go over that as best I can. This is going to be exactly the same, but then this is going to flick back up again. This is going to be exactly the same, but then this is going to flick back up again. So that's the shape of the modulus graph. Okay, part C then says using this model, so we've got HT now being used to model the height of a ball being kicked from the ground, the height of the ball reaches. So you can kind of imagine the ball being kicked from the ground and bouncing up in the air, but each time it bounces, it doesn't bounce as high as the previous time. It says, using this model, find the maximum height of the ball above the ground between the first and second bounce. So here's the first bounce and the second bounce. So we're being asked to find this point here. So that's the turning point, the second turning point of the function. So we're going to use the tan x equals 4 from the previous part and solve that, but we're interested in the second positive solution. So x will be the inverse tan of 4. We need to make sure that we're in radians for this because it's anything to do with differentiation and integration of trig needs to be in radians. And that gives me, for the first value, 1.33. We want, as I said before, we want the second value though. So for a tan graph, to get the next value on a tan graph, it's the simplest one. We add on, because the period of a tan graph is pi radians. We just need to add on pi radians. So 1.33 add pi is 4.47. Now that's just the value that the height happens, that the maximum point occurs at. We want the value of the maximum point. We want to know the actual height that the ball reaches. So we need to sub that into here. So h of 4.47, and I'm going to use the exact answer, so I'm going to use the answer button on my calculator, is going to be the modulus of 10 times e to the minus 0.25 times 4.47 times by sine of 4.47. And that gives me an answer of, because it's modulus, that gives me an answer of positive 3.18 meters. Okay, part D is then another one marker, and it says, why should we not use the model to predict the times of each bounce? Why is it okay to predict the heights but not the times? And without knowing what they want us to write, without having the mark scheme available to us yet, I've got two possible answers that they might be looking for. I'm not quite sure which one they're actually getting at. The two things that I can see is that this function is infinite, so this function will repeat and repeat and repeat. Yes, this will get smaller and smaller and smaller, but it will still give us values, whereas in real life that ball is going to stop bouncing. It's gonna become stationary at some point. So one possible answer is that the model suggests that the ball will bounce forever, which is obviously not true. But that's then kind of saying that surely it would still be okay for the first few bounces. Is that not okay either? And so that got me thinking about using models to predict values in general, and wondered if they're after the fact that it's okay to predict the y values, the dependent variable, but it's not okay to use models to predict the independent variable. So we're all right estimating values of h, but we're not all right estimating values of x. Similar to your applied maths, So I think maybe that's the answer that they're actually looking for. I don't know whether this would get the mark, but it might be that they're after us saying that we shouldn't, it isn't reliable, or it's not good practice to use the model to predict the controlled or independent variable. So I reckon one of those is the right answer, but possibly they'd allow both. But without seeing the mark scheme, I'm not sure which one they were actually.